Hi, this is Bill Foote again, and it is still Stats 1, and it is still Lecture 11, but now we're in Part 2. And this is what we did in Part 1, hypothetically speaking. We posed a question, in this case about quar prices. We could have just as easily done a favorite product launch of mine, Iguana Go Home, with International Compost and Compound Company of Billy and Myers fame in their famous or notorious or infamous principles of corporate finance course. We posed a question about prices, high and low markets. We sample a bunch of prices. We find that a price is whatever. And now we want to know which market is it from. Does it act more like a Sri Lankan market, which is typically and historically a low price quar market, relative to Indonesian markets, which are typically higher price? And the difference between them is probably insurance and freight, but we won't go into that issue. And we're talking about quar, of course, the brown fiber inside of mature coconut husks. Probably desiccated, but we won't go into that either. So we formed two hypotheses, low and high. We've sampled, we have some data, we've counted. Now the counting is, again, Gaussian counting. That's how we're counting things. Okay, that's how we're counting how often it occurs that a particular hypothesis can be said to have had, and that's a plausibility index, a probability. And going way back, remember, probabilities are between 0 and 1. And all the probabilities for all of the events that we're looking at, not all the hypotheses, all of the events would add up to 1. Probabilities across hypotheses do not add up to 1, by the way, right? Remember, yes, right? They're all very, very, very different. They're two different distributions in this case. So we're going to use that counting scheme instead of a binomial or a Poisson or perhaps an exponential, or some other interesting distribution like a half Cauchy or something of that nature. And we're going to do an inference. We're going to ask, which one does this sample belong to? It's a classification problem, typical of about everything we do in machine learning, for example. And we drew this lovely picture here saying we have a criterion. If the probability greater than that sample mean under the low hypothesis exceeds, that's the blue one, exceeds the probability less than that under the high hypothesis, then we'll say it's a low region. Okay, that's where we were. That's what we did. That was part 1. And now let's implement this in a model in part 2. Here's the model. Not too hard to see. Let me get rid of me here. You can't get rid of me. So this is the model. I want to focus on this lovely low versus high markets will be the title that we'll use. We have lined up, as we have all along, data on the top. Now the data here is just a sampled mu. That's what it is. And suppose it's 280. We'll play around with this, see how it works. 280 US dollars per metric ton. We have a low and we have a high hypothesis. We have a mu and a sigma for that hypothesis. It happens to be a low mu, low sigma environment. Could be just the opposite. We'll see how that works out. We have a way of counting, and that is the normal distribution, the Gaussian distribution, which takes into account what is the probability. That's the false thing here. Yeah. What is the probability of 280 occurring under the guise of the mu and sigma of 220 and 225. That's the condition. Those two cells, C4 and D4, are the condition. And the rest of the model says false is what? Probability distribution function. That's our method of counting. So we come up with this number for the low and this number for the high. Now, the probability of either hypothesis occurring, we're going to say in our framework, right now we're agnostic. We're indifferent. We're detached. How else can we put this? We just don't know. That's what agnostic means, 50-50. Okay. We may actually have a predilection for low markets occurring as opposed to high markets occurring. Some sort of clustering effect is very, very common in commodity markets and financial markets in general. And actually there, in many financial markets, we would be saying not prices. We often use returns because we're so sensitive to trends and deviations from trends and smoothing. And we're not going to do any smoothing here. Okay. So what is this 0.004? It is the probability that we see the hypothesis and the both and that this hypothesis is this probable, 0.009. 0.5, half of 0.009 is roughly this. Okay. We do the same for the high, 3, 10, 50. Compute the normal distribution based upon this sample. So we're mashing together, once again, we're mashing together data samples. That 280 is data versus our hypothesis. This is the high market hypothesis. Again, 50-50, we don't know. 0.0033 is the probability of that hypothesis, which is 50-50. And under that hypothesis, conditional on that hypothesis, we see this data. Okay. And actually, that is incorrect. That's data and hypothesis. Or go get it correct. This is the probability of seeing this data under this hypothesis. There we go. Conditional probability dyslexia. That's me for sure. Okay, now, as I said, this is a different situation than this. Different because of those values are radically different from those values. So we have to take these probabilities. If we want to look across either this hypothesis or this hypothesis can occur, this is technically the probability of the data. You add them together. They're mutually exclusive, okay, and completely exhaustive. Well, if those are the only two events we can look at, a low event and a high event, then the probability of seeing 280 is 0.0038. Okay, that's what that means. And then we can compute the relative frequency of seeing this hypothesis with this data versus this hypothesis with this data as 0.0004 divided by 0.0038, 0.0033 divided by 0.0038, and we get that simple arithmetic. Okay, 88-12 roughly, that's the split. Of course, they do add up to 1 just to show that. The odds of the low versus the high favor the high. Okay, they favor the high. I mean, it's equal to 6.5 to 1, 6.6 to 1. more likely to see the high than the low with a 280. Now, here's the rest of the story. Here's the rest of the consistent story. Here's the tail, greater than 280. The tail, less than 280. Tail greater than 280 under the low hypothesis is only 0.00282 probable. The tail less than 280 under the high hypothesis is 0.2743. We choose this one. There we go. Choose that one. It gives the same answer as the odds, but it's kind of a little bit more interesting answer from my point of view. And here's the picture down here where we have the low price environment in blue and the high price environment in, yes, red. Here's the sample, the dashed line. Look at this dashed line. Let me see if I can blow this up a little bit for you. This is what we're dealing with. This little wedge right here, that little wedge, very small wedge. That small wedge right there is the 0.00, whatever that was up there. What was that? 0082. Really small. Really, really small. And this wedge, much larger, 0.29. Okay, so using that logic, the high hypothesis definitely dominates. It's almost, we used to do this years ago, a stochastic dominance. Okay, 27% versus less, well, almost 1%. Okay, one is more plausible than the other. The prices, I mean, how do you get this price under this curve? You have to go from the left to the right. And how do you get the price for the other curves? You go from the right to the left. Okay. That's the idea, and we're going to stick with it. I just think it's a little bit more interesting. Because when you deal with cumulative probabilities, you deal much more with an expectational idea. Which one would you expect? You would expect, given all of the experience under the high curve, and it's an acid test. You're actually, look at where that wedge is. It's in the low region. So much of that orange curve is actually sharing region of price with the blue. And so little of the blue curve is sharing that same region with the orange. We choose the red. Okay, that's the idea. So anyways, if you like that idea, terrific. You can see that. Now let's see if let's play with this just a tad more. Let's put a price. Now this is obvious. Common sense should tell you. Okay, and that's one of the Edward D. James. James. See if I can get James up here. One of his 3 rules on probability has a logical approach here from R.T. Fox. One of the rules, it has to make sense. Okay, he calls it common sense. I don't call it common sense. I call it logical sense. But James, that's okay. There we go. let's put in something less than the 220. I mean, what is your expectation? What is your expectation? Okay, think just for a second. Oh, it could be a low price. We should have higher odds for the low than the high. And the probability of Y being greater, that blue wedge ought to be, given the low, ought to far exceed the high. Okay, that's what we should see. Now let's see if we do. Let's do it at 210. The 210 price, obviously a Sri Lankan price. You don't see 210 prices in Indonesia. Well, I don't know. Let's see what happens. Yes, correct. 13 to 1. Okay. Dominates. Okay, we switch this around. Choose that one. Okay. Again, just comparing the two. We see a very, very small red wedge, very large blue trapezoidal wedge. Okay. Makes sense, should make sense. Now, does it make sense in the other direction? I don't know. Anything greater than 310. Okay, make it 320. No, obviously. That's 100,459. Whose door number Indonesian. I mean, you know, that's what that is. Choose that. Okay, so you see that the two approaches are consistent with one another. So here's the sample, just to the right of the Indonesian average that we believe is out there. Almost, it is so little, it comes out zero, almost no wedge there. Look at this. I mean, it's more than half, right? More than half. Is it more than half? Yeah, it's more than half. 57%, 58%. Okay. Here's another one we can do. Just one more where we go home. Okay. What's the break even? Where the odds are 1 to 1, and let's look at these probabilities in that case. What do you think is going to happen? Okay. So to do that, use goal seek data. What if analysis, goal seek. And look what we can do. Set what cell? Set this cell equal to 1 by changing what cell? What would the sample have to look like is the question being asked here. And this little one parameter optimization routine will tell us. Look at what it did. Boy, wasn't that fun to watch? Not going to do it again though. Yes, we'll do it again. We'll see. Set this odds number to 0. Sorry, to 1, not to 0. Oh my gosh, what am I talking about? By changing the sample. Okay. This is what we would expect. Beautiful. Look, it went up and went down. Yeah, it's searching for extraterrestrial life here. At 258, at 258.9573, the odds are 1 to 1. But look at what happened here. We still would choose, but the probability, it's 3 times more plausible to have a high than a low. It would choose, in this particular case, the high and the low. So the odds don't always seem to work. Fascinating. In this particular case, that's a 1 to 1 odds. Oh my goodness. Well, let's compute this ratio. And they're equal. Okay, that's just the ratio of the high versus the low probability. So let's now do some different experiment and see what the odds look like there. So this is why we have to play with the models. Yeah, oh, we were patting ourselves on the back that the odds ratio of what we've been doing here will give us the right answer. Not necessarily, not if we believe this approach, which I think is the more comprehensive approach. But we got to think about that a little bit further. Epistemically, it is. And epistemic means in the process, the cognitional activities, the operations of coming to a conclusion. That is okay. I think this approach is a little bit stronger from a logical point of view. Okay, let's try this. Okay, so what if again? What if? Okay, what cell we're going to set? We're going to set this cell to 1. I don't know that this will solve, honest to gosh. By changing again this y. It does. It's 249 is the break even. 249. Very different number. And it's not where they cross. It's kind of interesting. It's this number right here. So here's the answer. If y is greater than that, that's the same. If y is less than that, they're the same. They're equally plausible. This is the true break even. Any price less than, don't look at this, don't look at this, that's cumulative probability. Any price less than 249 will favor the low. Any price greater than, you got to flip things a little bit. Any price greater than 249 will favor the high. Well, let's see if that's true. 249. Now, a price less than 249 is definitely 220. Right? 220. Do you agree? Yes. Okay. Oh, I did something very wrong here. Wait a second. Sorry about that. There we go. Okay. 220. Yeah, definitely. Okay, so that logic works. Any price greater than that 249, like 310. 19, no. 10. Yeah, that favors the high. Okay, so our logic works. So just go to a little bit to the left and to the right, and notice these odds. Yeah, it definitely works. 99 to 1. Yeah, right. Okay. So I mean, we're almost consistent, but it doesn't give you the right break even. I think that's the important thing. The break even odds overestimate the price. We have to use this new criteria. So that's for you to play with. Enjoy yourself. You can pull apart this spreadsheet sometime. And it is available somewhere on WGFoot GitHub at WGFoot's GitHub.com. So you go to GitHub.com, look up WGFoot, WGFOOTE, go to Stats 1, and start searching for Spreadsheet, and you will find it in materials more than likely. I believe that's where it is. You can check that out. This will reside there, and I don't know about you, but I'm having a ball with this. Finally, getting to use all of these tools. We're going to go one step further in the next lecture, in lecture 12, to say, what if our mu actually looks like this, like price. The average price looks like this, where we have some other factor. Okay, that could be interesting, huh? Yeah, right? Yeah, that could be fascinating. So we can play with that too. We have two parameters, A and B, to play with, along with sigma. Okay, this is going to be fascinating. Let's see if we can do this. We have to figure out how to estimate A and B, and under Gaussian rules, it's a pretty simple estimation. We're going to find out, for example, that B is going to be equal to the covariance between P and Q divided by the variance, or the standard deviation squared, of Q. It's going to be a fascinating trip. And if that's true under Gaussian rules, meaning Gaussian counting models, we can use exactly the same framework to ask the question, is B no different than 0? Or is it real? The same kind of question as this. Is B 0, or is B some big number or some smaller number? All right, in either direction. We can't wait to do that. Okay, so that's lecture 12. That's the next round. Enjoy. And I hope this was helpful. And again, thank you very much for your kind attention.